Greetings. Welcome to our 54th episode of the FGI podcast series. My name is Tim Stark, and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign. On today's episode, we're going to focus on our June 11th, 2024 webinar titled Reliability Analysis of Landfill Slopes, presented by myself and Jala Lin, who is a postdoctoral research assistant at the University of McCall. This presentation is based on some of the research that is included in Jala Lin's PhD thesis, which was completed at the University of Illinois at Urbana-Champaign. So Jala did all the work, and he prepared the responses to these questions. And these are questions left over from the live webinar and some questions that we received in the post-webinar survey that was sent out. Number one, for tropical soil slopes, do you have experience in estimating the probability of failure? Could you use the approach that we presented in the webinar? The approach is similar. You can use the same procedure, and it's really the procedure presented in Duncan 2000, which is cited in the webinar slides. You can use one standard deviation on each of the input parameters that you use to calculate your factor of safety for a natural tropical soil slope, such as soil shear strength, rainfall, which then will give you a high and low piezometric level in the slope, and then using the change in factor of safety from -1 standard deviation to +1 standard deviation of that parameter, you can calculate the standard deviation of the factor of safety. And using the standard deviation and the average or most likely factor of safety, you can calculate the probability of failure for a natural tropical soil slope. If you have additional boring information or conduct additional borings in laboratory shear strength testing or conduct field testing like conducting cone penetration tests, you can try to reduce some of the variability in each of those parameters, say soil shear strength, unit weight, groundwater level, and that will reduce your delta or change in factor of safety from -1 standard deviation to +1 standard deviation. And that's how you can lower the probability of failure for a natural tropical soil slope. Now, one thing since the webinar started doing is instead of reporting it as a probability of failure, if you take 1 minus the probability of failure, you get the probability of success. And that may be a better way or a more useful way for clients and owners to understand your calculations. So you would report a value of, let's say, 90% or 95% probability of success. And so if they want to be at 100%, then you reduce your delta factor of safety with additional testing and so on. And it may be better to focus on success, probability of success instead of probability of failure. However, if you have more questions about analyzing natural tropical soil slopes, please contact me. Okay, number two from the questions from the live webinar. What changes have you seen that would cause a failure after X amount of years in a landfill slope? And I'm assuming they're talking about a landfill slope because that was the webinar. In natural slopes, of course, we see this frequently because soils can soften from the peak strength to the fully softened strength, resulting in failure. So there's numerous case histories of softening of soils with time, and thus a failure after X amount of years. And in fact, Skempton has a case history in London Clay where the failure occurred over 70 years after the cut slope was created. But now focusing on landfills, the degradation of interface strength due to installation and waste filling can decrease over time. And that can occur as the relative displacement between the geosynthetics and the critical interface. So for example, the geomembrane and the drainage composite or the geomembrane and the geosynthetic clay liner, if those displacements increase with time, you'll go from the peak, past the peak, towards the residual strength if you're not already at the residual strength due to installation and waste filling. And some of the things that can cause additional shear displacement during the life of the facility are waste settling with time, just due to its compressibility, waste degrading or undergoing biodegradation with time, causing down drag on the liner system. So one thing we do recommend is checking the factor of safety with the strength you think is going to be operational at the end of installation and waste filling, and make sure that factor of safety is greater than 1.1 to account for any creep the slope might undergo with time, such that if the interface strength does reach its residual strength, you shouldn't have a failure. And so that calculation is with the large displacement strength from direct shear, use a factor of safety of 1.1. If you use a true residual strength from a ring shear device, or you extrapolate the direct shear test data out to the true residual interface strength, then you can use a factor of safety just slightly above 1, because you know the interface strength won't drop below that residual. Okay, number 3 from the live webinar. Have you conducted any flak analysis on a landfill with symmetric right and left side slopes for comparison? Not all landfills have the same geometry as the Kettleman Hills hazardous waste facility in California. The short answer is we have not. The parametric study we showed the results of uses the Kettleman Hills geometry, and that's a base and a side slope. And so that's what we use to estimate whether you would be mobilizing a peak, large displacement, or residual interface strength at different side slope angles and side slopes lengths, which I'll talk about in just a minute. Okay, number 4 from the live webinar. For calculating a range of factor of safety when varying the residual interface strength, is the large displacement strength a most likely value? No, it is not. And this gets to the flak analysis that we did conduct on the Kettleman Hills geometry. There's a table in slide number 24, 33, and 49. There's a table on those 3 slides that show you the slope inclination of the side slope, 3:1 to 6:1. And then the length of the side slope varies from 80 meters to 240 meters long. So a short side slope to a long side slope. And that table shows you the interface strength that's mobilized at these different slope angles for the side slope, as well as the length of the side slope. So for example, if you have a flat side slope, 6:1, and it's a short length, you could mobilize the peak strength along the side slope. However, most landfill slopes are not at 6:1, they're usually around 3:1. And if we go to 3:1, even at the shortest length, 80 meters, you're at the large displacement strength. And then the 160-meter long side slope, you're between large displacement and residual. And for the long side slope, you're at residual. So the large displacement strength is not the most likely value or the average value. It depends on the length of the side slope and the inclination of the side slope. So don't just assume large displacement will be okay, because you could be in a situation where a residual is mobilized on the side slope. Okay, and the table on slides 24, 33, and 49 in the PDF that's on the FGI website will show you what strengths are mobilized along the base as well as the side slope. Okay, number 5 from the live webinar. For a flak analysis involving municipal solid waste, what constitutive model do you recommend for the municipal solid waste? In the analysis, we used two constitutive models, the Moore-Coulomb model and the modified Cam-Clay model. Based on that comparison, we recommend using the modified Cam-Clay model that's built into FLAC to represent the compressibility of municipal solid waste. So use the Cam-Clay model. Okay, now shifting to the questions from the post-webinar survey, and there are a lot of these. So thank you everybody for sending in questions. Okay, number one, follow-up survey. Using the range of interface shear strengths from the floor to the side slope assumes that the displacement has or will occur. Correct. That is correct. And that's because municipal solid waste is fairly compressible. So as it sits on the side slope, it is basically compressing under its own weight and down dragging on the side slope liner system, causing shear displacement. Is assuming a displacement of a certain magnitude does occur a fundamental basis for this approach? Yes, you can say it's assuming a displacement, but what we're doing is assuming that a certain interface strength develops on the side slope due to the inclination and the length of the side slope based on prior failures in which we've back calculated the mobilized interface strength, and also the FLAC analyses that I just described. Next question in this same question, doesn't the displacement at peak strength have to be overcome to reach post-peak and beyond strength? Yes, it does. But that is usually pretty easy with a, I won't say steep, but 3-to-1 to 4-to-1 side slope. And that peak strength is mobilized at a really small displacement, usually about 1/10 of an inch in the laboratory. So that displacement can be overcome, and then you're going down the post-peak and then out towards residual. And that's been verified with FLAC analyses of a case history that we used in this presentation, as well as a parametric study. In general, the peak strength is overcome during construction and waste filling. And then so you're operating at a post-peak strength after the landfill is constructed and waste filled. Okay, next. Van Mark 1977 proposed a way to further correct the probability of failure based on the scale of fluctuation and variance reduction function that would reduce the log normal or normal distribution of factor of safety. Do you see a potential for that? If we use compaction control or field QA/QC data to further continue on this topic and helping the engineers of the future. Thanks for your work. Regards, Evandro Jimenez. So Evandro, thanks for attending and thanks for a great question. Yeah, I think we can go back to Van Mark 1977, and in particular, the analysis we presented in the webinar assumed, better for worse, a log normal and a normal distribution of the factor of safety. And that's generally what the geotechnical profession assumes the distribution of factor of safety is. It doesn't have to be. Other people have used some different distributions like the beta distribution of factor of safety. So I do think there's some uncertainty in the probability of failure that we are calculating because we're assuming the distribution. However, in the webinar, one way we hope to control that uncertainty is by increasing the quality or consistency of the geosynthetics and the geosynthetic interfaces. So if we consistently produce geomembranes with the same texturing or the same asperity height, we'll reduce the uncertainty in the interface strength. And if we reduce that uncertainty, of course, we reduce the probability of failure. So I think it's kind of a combination of both, looking at different distributions of factor of safety as well as trying to produce more consistent geosynthetics. Okay, number 3 from the follow-up survey. Have you conducted any FLAC analyses with symmetric right and left side slopes? So that is similar to a prior question that I just answered. We have not. We've kind of used the Kettleman Hills case history as the for the parametric study. Okay, number 4 from the post-webinar survey. How do you recommend slope stability analyses for the berms that are used for flood protection of vital facilities? What is the acceptable probability of failure to consider? If the soil from the site has been used, how can we capture uncertainties in shear strength of the compacted material used for the embankment? Okay, great question. And we covered a little bit of this in slide number 14 and 15, which gives you sort of allowable values of probability of failure. Now, for dams and levees, and it's really for dams, and this is based on Whitman 1981, this is slide number 14 that I'm looking at. And notice for dams, he uses an annual probability of failure of 1 times 10 to the minus 4. So in other words, if you calculate a probability of failure greater than 1 times 10 to the minus 4, you are in the unacceptable range. You have to be below 1 times 10 to the minus 4. Okay. Let me make sure. How can you capture uncertainties in shear strength of compacted material used for the levee embankment? So this is an interesting topic because levees are generally extremely long. So what happened on the Dallas floodway project, the question was, how do we calculate or measure shear strength for 48 miles of levee? And so, make a long story short, the Army Corps of Engineers decided to use my fully softened and residual strength correlations for those levees. And all they had to do was measure Atterberg limits to use the correlation, because the correlations are based on liquid limit and clay size fraction or plasticity index. Now, before they could do that, you have to, quote, anchor the correlations. In other words, there's 136 soils tested in our correlation. And of course, that's not all soils in the world. So you need to make sure that the correlation is applicable to your levee project, in this case, the Dallas floodway. So the Corps of Engineers conduct an extensive direct shear testing program in which they measured the Atterberg limits of the sample, tested the sample in direct shear, and compared the results of the correlation to the direct shear value. And it was really good agreement, and so they decided to design the raising of the levee system based on the correlation. And so all they had to do was measure Atterberg limits for the 48 miles after that. Okay, and to anchor the correlation, I recommend that you test one soil from each of the 3 clay size groups or clay size fraction groups. There's a low clay size fraction, medium, and high. So don't just test one sample because the correlation could be bad for a low or medium or high clay size fraction. So test at least 3 soils and make sure the correlation is applicable to your levee site. Okay, number 5 from the survey. Let's see. This may have been answered during the webinar, and it looks familiar to me. For the landfill slope, when calculating variation in factor of safety for residual on the side slope, is the base strength held at the most likely value? And what that means is the base and then the side slope goes up the side. The base is held at the most likely value for that interface strength. So for example, if it's a short side slope, you'll have peak on the base. So you want to use the most likely value peak on the base. But then you have uncertainty in the peak. So you would have the plus or minus 1 standard deviation on the peak. and that contributes to the delta factor of safety for interface strength, and then thus the probability of failure. And then the question goes on. Similarly, for calculating the variation of factor of safety for large displacement strength on the base, is the side slope held at the most likely value residual? So if you're going to apply large displacement on the base, so that means you have a steep side slope and a long side slope, and you're applying residual on the side slope, you calculate the most likely value of factor of safety for that situation with the most likely large displacement on the base and the most likely residual on the side slope. Then you go plus or minus 1 standard deviation on the large displacement and the residual to calculate your delta factor of safety. Okay. All right. Number 6 from the follow-up survey. It is often the case that interface friction is characterized by literature values, not from tests adopted to a particular case or site. What is your recommendation in that situation? So I don't recommend using laboratory literature values. I recommend using laboratory values because the geosynthetics do vary. And notice my answer to one of the early questions is one of the things we need to improve is the variability in the geosynthetics. And for example, the variability in the texturing of the geomembrane. So I don't recommend using literature values. I recommend obtaining samples of the material that will eventually be shipped to your site and using those interface strengths to verify your design before the materials are shipped to your site. Once the materials arrive at your site, it is difficult to change the material. So test that material before it's shipped, and then you can get the plus or minus 1 standard deviation on the peak, large displacement, and the residual, and see if that yields a suitable probability of failure for your design before the material is shipped to your site. Okay, number 7. You've shown failures through the bottom liner system. What about cover liner failures, where often inclinations of 3 to 1 or less apply? So if you're talking about the final cover system with the geomembrane, final geosynthetic cover system, you can use the peak interface strength for the cover system. And that's because in the cover, the shear displacements are limited during construction and placement of the cover soil over top of the cover system. And those displacements usually do not take the interface past the peak. And that's the really big difference between the cover and the bottom liner systems. Okay, number 8. What about earthquake and factor of safety limits? So, good question. Use the maximum earthquake level for your particular site, and then you can use the most likely value for the peak ground acceleration to calculate your pseudostatic factor of safety. But then you can use plus or minus 1 standard deviation of that peak ground acceleration to get your delta factor of safety for seismic loading. And then using that delta factor of safety, calculate the standard deviation and probability of failure. So you can do the same analysis and include seismic effects in it. And you'll see as the range of peak ground acceleration varies, or pseudostatic seismic coefficient varies, you'll see the factor of safety will vary, and thus the probability of failure will vary. Okay, next is number 9 from the follow-up survey, and geez, there are 14. So number 9, do you know of an application of the proposed reliability of landfill slopes approach to natural and or man-made slopes, mining and civil engineering dams, or is it mainly landfill slopes? This same analysis can easily be applied to natural slopes and man-made slopes. Easy, and I talked about it at the beginning in the first question, applying it to tropical soil slopes. Same thing, just take your range in strength, your range in piezometric level, range in water content, calculate your delta factor of safety. You can use our correlation spreadsheet for fully softened and residual strengths, which you can download from the FGI website or my personal website at tstart.net, tstart, one word, .net. And we will post that spreadsheet with this webinar. And so you can go in and use your ±1 standard deviation on liquid limit clay size fraction, get your range of fully softened and residual strength, and calculate the probability of failure for your man-made slopes or natural slopes using the exact same analysis. Okay. Number 10, do you think the proposed approach presented could benefit of a correction using the scale of fluctuation? And it references a paper, by Van Mark, 1977. Yeah. So I think this is similar to the question I answered before, and I think it can. There is uncertainty in assuming a log or normal distribution of the factor of safety. So it might be beneficial to look at the fluctuation due to different distributions. However, if the landfill case, if the failure is mainly within the waste, so remember that's a non-homogeneous mass, that could add a lot of uncertainty because of the variability in the landfill mass. What makes the analysis that we presented so easy and applicable to landfills is generally the failure surface goes straight down to the bottom liner system and stays in the bottom liner system from the top to the toe of the slope. And that's because the municipal solid waste has turned out to be a very strong material. And so generally the failure does not occur within the waste. It's along the geosynthetic interface. And so it's really not that big of a variation along the geosynthetic interface. Only variation is due to the difference in texturing and geosynthetics from the top of the slope to the toe. Okay, number 12. Do you think the proposed approach presented could be expanded to natural or man-made slope if a large database of construction QA/QC and borings is obtained and utilized? And with the help of artificial intelligence coming on, could you facilitate implementation of this database for calculating probability of failure? I think the answer is yes. And the only caveat is all of that information, the construction QA/QC and the borings, really has to come from nearby the site you're considering, because soils do vary. So I'd be careful of natural soils varying. Now, if it's in terms of geosynthetics, maybe this can work if you use the artificial intelligence for one manufacturer. So in other words, you create your database of construction QA/QC and bottom liner system interface strength if one manufacturer is involved. And if it's only that one manufacturer, maybe you can use adjacent sites if the materials are produced in roughly the same time period. In other words, you can't use newly, say 2024 geosynthetics and use data from a site that was lined 10 years ago, because the manufacturing process probably isn't the same. But I do think that that could be a potential advantage for future analysis. Okay, number 13. Curious how you have such a low variability in your waste shear strength on slide number 20. Slide number 20 presents some failure envelopes or strength envelopes for your municipal solid waste that we've developed over the years. And the way we developed those was using landfill slope failures. Oh, actually, it's slide number 29, not 20. Slide number 29 And you'll see a lot of data points on that plot. Some are from landfill slope failures where we back calculated the waste strength. The other data points are from laboratory direct shear tests on municipal solid waste. So there is a lot of variability, and the strength envelope that we used in the analysis is sort of the most likely value. So if the failure surface in the case that we presented stayed in the waste, we would have had to take into account +1, -1 standard deviation of the waste strength, which would have been a very large range. And that very large range would have given you a very large delta factor of safety, which would have given you a high probability of failure. So the beauty of the calculation in this case history that we presented is the failure surface went straight through the waste at the top where it was fairly thin, into the liner system, and stayed in the bottom liner system all the way to the toe. So in short, there is a lot of variability in the waste strength, but if the failure surface stays in the bottom liner system, it really doesn't affect the probability of failure much. Okay, last question from the survey. When adjusting input parameters, I assume you only change one at a time. Correct. Only one at a time to calculate the delta factor of safety for that parameter. So let's take unit weight. Let's use a unit weight of 100 pounds per cubic foot. So if I go ±1 standard deviation, maybe that's 85 to 110. So I vary from 85 to 110, and I calculate the delta factor of safety. All other parameters stay constant. So that gives me delta factor of safety of unit weight. And then I can do the same for shear strength, piezometric level, and so on. Add those together, and I get the standard deviation of the factor of safety. Okay, that's all the questions. If you still have additional questions, please contact me or Jala Lin. His email message is also in the slides, in the first slide and on the last slide. So thank you to Jala Lin for conducting this research as part of his PhD at the University of Illinois and helping me answer all of these excellent questions from our webinar. So everybody, thanks for joining us, and I hope to see you on our next webinar.